Welcome, everyone. We are truly delighted to have you with us today as we begin another thought-provoking chapter of Rextra 2025, the Silver Jubilee Tech Showcase organized by the Faculty of Engineering, University of Ruhuna. This initiative is the one that celebrates 25 years of academic excellence in the Faculty of Engineering, University of Ruhuna. As part of Rextra, we have lined up a series of insightful webinars covering a wide range of cutting-edge topics, from renewable energy, quantum computing, and sustainable infrastructure to AI-driven technologies, marine energy, and personal branding in the digital era. So these sessions aim to spark meaningful discussions and open doors to the future engineering and beyond. So before we dive into today's session, let me introduce myself. I'm Tinma Vidanage, a first-year undergraduate from the Faculty of Engineering, University of Ruhuna. So I'll be your moderator for today's session. It's truly an honor to be the moderator for this thought-provoking session, and hope we all get together and dive into the session. So to officially open, I would now like to invite Professor Chaminda Karunasena, Dean, Faculty of Engineering, University of Ruhuna, to deliver the welcome speech and share a few words with us.
Thank you very much for the generous invitation. And I'm very delighted to address you all on this auspicious occasion where Faculty of Engineering, University of Ruhuna, marking its 25th of years of excellence, celebrating the Silver Jubilee. So in this regard, we are starting this webinar series, and so as a beginning, we are starting the first session today, having one of the leading characters in renewable energy and electrical engineering in Sri Lanka, Professor Janaka Ekanayaka, Senior Professor Janaka Ekanayaka. And on behalf of the faculty, I would like to mention that we are delighted to celebrate this great milestone in our track record as a faculty. And Ruhuna is no more younger faculty, and we are ready to take more challenges, becoming international quality in teaching and research, with enough collaboration with all our fellow universities, faculties, engineering faculties, locally and global. For instance, today's session, we invited none other than Senior Professor Janaka Ekanayaka, who is from Peradeniya Engineering Faculty, and we all are responsible to build next generation talented, qualified engineers who can solve real-world complex engineering problems, making our clients happy while making the nation outstanding among any other nations. So in this backdrop, Faculty of Engineering celebrates its Silver Jubilee, while the Rextra exhibition scheduled on December 5th to 7th will be our grand finale event. Before that, as a social commitment for our nation, in this juncture where as a nation we are upgrading our capacities, building infrastructure, different new policies, reforms, many things come. And as engineering practitioners, learning and higher educational stakeholders, we have also a role for new avenues to show what engineering can do and what are the latest trends and where as a nation how the directions we can proceed. So in this broad purview, Rextra organizing committee took a decision. I think it's very critical decision that have this kind of open seminar series, allowing general public and practicing professionals and well-wishers to get immersed in engineering latest trends. And we are glad to have one of the outstanding experts and very senior academic in Sri Lankan academia in engineering generously accept our invitation and spending this valuable time on behalf of this Rextra event series. So with that brief note, I warmly invite our resource person to proceed, and hope everyone you will join hands with our Silver Jubilee celebrations, and all our graduates, current students, staff, and our fellow academics in all the state and private universities and industries. Please join hands with us, and let's get together and celebrate this Silver Jubilee while making Faculty of Engineering recognized as a matured enough faculty who can work collaboratively with all other institutions and industries to meet with international and local requirements to drive the mother nation towards the development, which is top priority. So in this endeavor, I hope this is our official very first technical event, and I hope it would be an outstanding experience for everyone. So with that short remark, thank you very much again for having me today. So over to you all. Thank you.
Thank you very much, sir. So today's webinar, Smart Grids, Renewable Energy and Energy Storage Breakthroughs, is not just an event. It's a journey powered by intelligence, sustainability, and cutting-edge technology. So in the next 2 hours, you will witness groundbreaking concepts, explore real-world solutions, and gain insights from one of the most respected experts in the field. So get ready to learn, engage, and be inspired as we move towards a smarter, greener energy future. It is now my honor to introduce our distinguished guest speaker, Senior Professor Janaka Bandara Ekanayaka, a renowned academic and expert in the field of renewable energy and smart grid technologies. With his vast research contributions and leadership in sustainable energy innovations, he has been an inspiration to both academia and industry. We are truly privileged to have him with us today. So I now warmly invite Professor Ekanayaka to deliver his session on smart grids, renewable energy, and energy storage breakthroughs. Over to you, sir.
Can you hear me? Hello, can you hear me? Hello? Can you hear me?
Yes, we can hear you.
Yes, sir, we can hear you.
Now it's okay. No, I have different speakers, microphones, so I need to select the correct one. Okay, let me share my slide. I can't share. Can somebody give me access, please? Okay. So can you see these slides on full screen, or is it coming as...
Now we can't see the screens.
You can't see?
Yeah, we can see the screens.
Is it the full screen, or is it comes with the notepad kind of thingy? It is full screen, is it? Can you see my next slide, or only you see one slide?
Not only the one side, sir, we can see the whole screen with speaker notes and whatnot.
Okay, so let me, if I do that,
Now it's yours.
Okay. Okay, so thank you very much for inviting me to deliver the first lecture on this Silver Jubilee lecture series. I really appreciate the Dean and the organizers for giving me this opportunity. I will talk about some of the aspects. Of course, this is a vast area, but I will try to talk about a little bit about sustainability, and then move on to barriers for sustainability, and then some solutions, and will then draw a few conclusions. Now, what happened if you look at the past? In 19th century, we start using water power mainly to the run industries in Western economies. But slowly, that renewable portion became smaller because we burn more and more fossil fuel with the transportation, and there is a living standard in Western economies in rises, and then rapid industrialization on China and so on. So, if you look at the picture today, we have major portion of our energy comes from the fossil fuel. Towards the future, we don't want to see any increase in the energy demand. Whereas we wanted to increase the renewable energy portion. Remember, I'm showing you not the electrical energy here. I'm talking about the total energy. So in order to achieve constant demand, we need to increase the energy efficiency. And one way of doing that is today moving towards more electrical usages. So I'll come back to that. Then, of course, as I said, in order to achieve that efficiency, we electrify many things. We electrify the road transport, we electrify the heat, and so on and so forth. Now, at the same time, we need to see that we are utilizing renewable energy more and more. So we will be increasing the blue portion of this figure. Now, the climate action outlook says that if we go along with the renewable path, there will be 4.2 trillion annual savings by 2030, 80% reduction in the cost of electricity, 99% reduction in the pollution, and 30 million new jobs. Now, how much these figures we can achieve depend on whether we can make our system sustainable. Now, the sustainability should come just not only looking at the environmental growth, the sustainability, we also need to see economical sustainability as well as the social sustainability. So, as you can see in this triangle, should move in all directions. But of course, there are barriers. Now, one barrier is the unprecedented increase in demand. Now, something new has come. I'm sure most of you are now using these tools every day for your day-to-day learning activities as well as for your day-to-day home activities. If you want to write a letter, you go and consult one of these ChatGPT tools. So, have you ever thought about the negative consequences of this one to the grid? Now, remember, the new mega hyperscale data centers required at least 100 megawatt. which means like more than 400,000 electric vehicles. So you can see that when you use these tools, we are basically loading the data centers either in United States or in China or somewhere. So basically, we are burning lots and lots of energy. Now, it's forecasted that the global power consumption of data centers will double between 22 and 26. The second thing we are noticing is the major much increase in the electric vehicles. Of course, if you go out, you will see many BYDs now hanging around. And this also has increased over the years, and they are expected to increase more and more and going to impact on our electrical system. So we like in the if you compare the 2023 and 2024, there are more than 3 million increase in the car sales. Now, this shows the expected electrical energy consumption in terawatt hours. Remember, Sri Lanka's energy consumption is only 20 terawatt hours, whereas we are seeing here by 2030, the required energy consumption of EVs will be around 800 terawatt hours. So that's another issue we need to tackle. So we are trying to electrify, but at the same time, the impact on the electrical networks is increasing hugely. There's one more thing. When we go for renewable addition, there will be a paradigm shift. Before talking about the paradigm shift, let me introduce you some of the latest renewable additions we have. Now, the wind power has now become a mature technology. Somewhere in 1990, I started working on wind turbines, that was fixed speed induction generators. And we had our very first wind turbine in Mirijavilla, Hambantota, which is no longer there, which was a 600 kilowatt fixed speed induction generator. Then there was a time where the double fed induction generators, which is mainly the wound rotor induction generator, fed by two back-to-back converters emerged. And I mean, if you look at my research, they are mainly started in that era. And then, of course, there was a change in the generator technology. We start seeing full power converter gear technologies coming up as 3.5 megawatt. However, these gearboxes are very heavy. If I just give you an idea, the bonus 3.5, the generator, the weight of the generator is 13,000 kilogram, and weight of the gearbox is also 13,000 kilograms. So these large cranes that are carrying the nacelle up to the top of the tower, you see, like it's a 100-meter tower, so you need to carry this nacelle, which has 26 kilograms for the generator and the gearbox, plus all the other things could be around 40,000 kilograms. And because of these limitations, people start looking at other variants. And today, most of the generators are permanent magnet full power converter, where you don't use gearbox anymore. You don't need to use gearbox because the permanent magnet machines, which are having like 100 poles, and if you could remember your basics, the synchronized speed is 120 F over P. When P is very high, you can operate at a very low speed. Remember, the wind can only rotate your turbine at around 100 revolution per minute, whereas the conventional generators with 2-pole or 4-pole required you to rotate the generator at 1,500 or 3,000 revolution per minute. So if you have 100 poles, then you can directly connect your turbine to the generator and you don't need a gearbox. So you can see the largest wind turbine today mainly used for offshore applications, and it is also been compared with the largest aircraft in the world. So you can just imagine how big these giants are. Of course, the offshore industry was booming at one point. Of course, now it's kind of sleeping a little while. So what you do is you uh, put up a substation onshore, then put it on a ship and take it to an offshore platform. Now, there's interesting story about this part. Um, Now, there are only few, I mean, talking about few years ago, there are only few ships which has a crane and which can carry this on offshore substation. Remember, the substation has switchgear, generator, transformers, and everything that you see in a normal substation. So you need to book these ships well in advance, and these ships ask for the full payment. And if you can't take your offshore platform on the day that you planned due to the stormy weather or something, you are going to lose all that money. So there are lots of mathematicians working with these companies. They're kind of not, I would say, the engineers with lots of talent in mathematical modeling to model the sea and to make sure that the day they are planning to shift their uh, substation is a good day for ship to travel. So this is something like in most of these cases, the standard engineering parts are very simple. What we need to do is either think about the innovative foundations, or think about how to bury your cables and so on and so forth. So these are multidisciplinary groups working on these offshore wind power projects. The PV technology also booming, even though the 90% of the usage is crystalline silicon. Other technologies are also coming up, such as gallium arsenide, multi-junction. I'll show you multi-junction in a minute. Amorphous silicon, cadmium telluride, carbon, indium, gallium, sulfide, and so on. And there are some emerging ones, especially perovskite, which is a new material which was found, and Oxford is working on the solar cells, and these cells are very promising today. And then, of course, there are other cells which are very small in size, organic diselenide and quantum dot. Now, the multi-junction PV cells are special. What you have is on top of the PV cell, you have a prism. The prism breaks the sunlight into different wavelengths. The very first wavelength will go to a gallium indium phosphate layer. The second waves will go to gallium arsenide layer, and final lot go to a germanium layer. Remember, as you can see from the figure, silicon can only capture part of that spectrum. So by using this multi-junction, you can capture high frequency part of the sun spectrum. And this one shows the NREL's figures of the efficiencies. As you can see, multi-junctions has reached somewhere around 47%, whereas the silicon is somewhere around 20, And the perovskite, which has very recently started, this one, I think, has reached the silicon value. Well, silicon is 27, reached the silicon efficiencies within very few years of time. So these technologies are improving every day, and the cost of the technologies come down. Used to be dollar per watt, but now it's less than $0.25 per watt. Of course, the prices varies country to country. And I started by saying that these renewable energy sources introduce a paradigm shift, and let me introduce that now. Now, what we had was we had storage. So we take the resource, could be water, could be diesel, could be coal. We store them and we use them whenever we want. So we basically following the load and we generate as just above what is required. But and today we can't store the renewable energy. So only way is to store the electricity. For that, we need energy storage. However, the energy storage are expensive, and one of the solution which other countries used was the pump hydros. You use a generator plus pump. During the time you have lots of solar, you pump the water back to the upper reservoir, and during the time during the night, you let the water to come down to the penstock and rotate the generator. There are few in UK, the Dino, which is the largest, around 1.72 gigawatt. So we are now doing some studies, and we are planning to have pump hydros, but in my opinion, now it's very late to start a pump hydro project because the energy storage prices are coming down. Now, this is another issue with the solar additions. When you add more and more solar during the daytime, the demand seen by the grid will come down. Now you can see that this is the South Australia. These are the minimum demand days. On 2006, somewhere around 12 noon, the demand was 953 megawatt. But in 2019, it has dropped to 62 megawatt. Now the main issue is the grid won't see this. The system operator won't see. They don't have the visibility. They don't know how much generation is at each home. Unless you have ways of getting that information. I'll come back to that in a minute. So when you have that kind of a scenario, and if there's a cloud cover, this is going to suddenly increase. And the grid should be ready to supply whatever this demand. And that is exactly what happened. If you could remember, one of the blackouts, we had a similar situation. Other issue is, of course, the coal is a plant which is inflexible. And with the renewables, these inflexible power plants cannot survive, because you can see that in UK, they are daily cycling coal power plant, but there was a period on this was in 21st April 2017, the coal power plant has to be spinning for 24 hours without generating. So this is a huge impact. Other problem is the system loses its inertia. Remember, inertia is something given by the rotating masses. Now, when you don't have rotating masses such as solar, the wind, even though it's a rotating mass, it is the wind generator is decoupled from the grid through two back-to-back converters. So they all does not provide any inertia. And having a low inertia is also one barrier. For example, this shows an event happened in the UK. Now, on this around this time where I'm pointing, There was a generator loss due to a natural scenario. With that, the frequency drops, and second generator to start trips. And the free, as you can see that because there were lots and lots of wind and embedded generation, the frequency start dropping at a higher rate because of the very low inertia. With that, these embedded generators will start tripping off because they were not supposed to be on the system. And that created almost a blackout. But of course, as I told you, UK has the pump hydro, which can move from pump into generation within 12 seconds. So it can bring the frequency back very quickly. Another issue which was happened in Australia. Remember, the blackouts that are happening in Sri Lanka is pretty much straightforward. These are what I'm showing you is very difficult to find out kind of blackout, but they did find it out. Now these wind turbines are supposed to have what we call the ride-through capability. What it means is whenever there is a fault on the grid, they should, of course, spin without producing any energy, any electricity. But immediately after the grid fault is cleared by the protection, it should come back and supply power. You can see here, this slot has come down during the fault, but immediately after that, it has come back. Same with the green one, same with the blue one, but not the red one. So that was something due to the not setting the fault right through capabilities properly. But now, of course, South Australia is putting very stringent guidelines for wind turbine operators to make sure that they all ride through faults. This is another very difficult scenario which was found by the UK utility. The London, which is further down here, had a partial blackout in August 2019, and they found that is due to a wind farm far away. Hornsea is not anywhere closer to London, but that wind farm was the culprit, and they found that. So as a solution, the smart grid came up. Remember, there's nothing called smart grid. Smart grid is basically a collection of technologies. We already had the network layer, which has been there since inception of the grid. On top of the network layer, we start seeing the power electronic. Initially, we start with the Mercury arc rectifier. Maybe the only working Mercury arc rectifier in the world is at Peradeniya. So if you are coming to see the exhibition, please make sure you look at that. Then the Mercury arc rectifiers were replaced by thyristors, but today you mainly use IGBTs and various new devices. So the power electronics start to help in the grid in many ways. Then came the renewable energy and energy storage. Now we have introduced lots and lots of sensors on our network, which are mainly smart meters, VCTs and VTs we already had, and the PMUs. On top of that, you connect these sensors using an ICT layer. Inside the substation, you use IEC 61850 protocol. And for the home, you will have various different protocols. And there are a couple of networks operating in Sri Lanka. One in Negombo operating on power line carrier, and one in Katunayak operating on Bluetooth. And I'm sure there are more now. And then we start seeing the distribution automation and finally modern control center. In fact, if you look at Sri Lanka, we have the network layer, we have the modern control center, but most of the middle things are missing. So we can't have a fully fledged smart grid operation. As I told you, there is no particular definitions for smart grid. Smart grid is defined by different utilities depending on their requirement. For example, European technology platforms say a smart grid is an electrical network that can intelligently integrate the action of all users connected to it, generators, consumers, and those that do both. That means, like many people, like even the faculty now has solar, so we call them prosumers. In order to efficiently deliver sustainable economic and secure electrical supply. So likewise, different people define the smart grid in different ways. So if you wanted to go in this direction, we should have a very clear smart grid roadmap, and we must define what we want. Now, these smart grids will enable real-time visualization of the power system, support enhancement of power system security, relieve system bottlenecks, enable self-healing, and enable connectivity to consumers. So let's go one by one. To enhance the visibility, of course, one technology we use is the smart metering technology. However, you can have the full visibility of the network. The home area network are the one which is using the smart meters. There can be neighboring area network using the concentrators of the smart meters. Then the substation LAN uses IEC 61850. Then there could be a wide area network with PMUs and so on, as you can see in many other countries. Now, the smart meters basically connected to each home send signals depending on the time duration to a concentrator. Concentrator sends, all the concentrators send their signals to a super concentrator, and then it goes to the control center. And control center can send signal back to either switch off your car charging or to switch on your PV generation or whatever. So that is not there in Sri Lanka yet. So if you look at a smart meter, it's a digital device, but the main thing is it has a on top of the metering units, it also has communication unit and various other measuring devices with lots of storage. So usual configuration is you have the smart meter, which has its own little data storage, but every depending on the protocol you set, the smart meter sends data to the data concentrator, and data concentrator sends the data time to time to the advanced metering management system, and from there it goes to the meter data management system. So this system used to be with CEB and LECO, and we still have exactly the same structure. And as you look at the communication standard for smart meters, there are plenty. So I'm not going to go into detail. This is for completeness because I can see that you are recording, so you can look at these in leisurely. And also the smart meters offer various near real time and the more long term support to the grid, and I will come into one or two later on. Now, one of the things is as we are having more and more power electronic devices, there's a fear that we can't form the grid. Black start is not easy. So there are now practically implemented system to form the grid. So you basically use the AVR and the frequency governor to form the grid. At the same time, there are this is basically the response of the grid forming inverter versus the synchronized machine. So you can see that you can have a smooth grid forming with these grid forming inverters. All the other inverters act as grid following inverters. Now, energy storage will become one of the main requirement when you have more and more renewables. And today you can find energy storage with different power densities and energy densities, but mainly used devices are lithium ion, hydrogen fuel cells, sodium sulfur, and little bit of flywheels, but others are, and also as I told, pump hydros. But they're depending on the applications you can use. For example, this is a wind farm in Japan. The wind turbines altogether generate 51 megawatt. In order to support this wind farm, they have sodium sulfur battery of 34, two-thirds of their requirement, and they are connected through a converter substation to a control building. And what you are seeing here is the yellow one is the wind farm output. As wind varies, its output varies. And the blue one is the scheduled power required by the grid. So you can charge the battery or discharge the battery and make sure this black dot says that you can follow the grid requirement perfectly if you have large amount of energy stored. Same if you look at the countries like Japan, this is on one particular day in Japan, you can see their demand is this red curve. They have the pump storage hydro and batteries. So the solar generation is this black dotted curve. So most of the solar is stored and then utilized later on. So that is possible. But even with that, you have to curtail around 1 gigawatt because they don't have enough storage to absorb that. Of course, you can use electric vehicles as distributed energy storage. Every vehicle today has V2G or V2L facilities. So you can use them also as a energy storage. Now, the demand side management is something which is required. I don't know whether this will work. Let me see. Yeah. Yeah, this is the problem with HDMI. Maybe I need to share it in a different way. Let me give me a second. I think I need to share as go to advanced and it's advanced. Let me try. Let me skip that video because I spend more time to fix that while we are. No. Okay. So basically what this shows is it's a company in US. They are matching the supply and demand using the demand side approaches. So they have various ways to. Okay. It's good. So that's just a demonstration of one particular utility. And to relieve the transmission bottlenecks, we start using HVDC. Now remember, you know this equation P equal to V1, V2, X over sine delta. Now with the power electronic, you can change any of these. The voltage can be changed by STATCOM or SV's static VAR compensators. We do have one in one in somewhere, I can't remember now. And we can use the series capacitor or thyristor control series capacitor to control that X. We can change the angle delta by using phase shifting transformer. But on top of that, we can add a high voltage DC link in parallel to the AC link to increase the power transfer capability. Now, remember the DC becomes cheaper than AC at a distance around 50 kilometer if it is submarine, 800 kilometers if it is overhead. There are applications of HVDC, and you can also see that the 3-core 132 kilovolt AC cables required to transmit 1 gigawatt, you require 5 cable of that size. If you want to use DC with plus or minus 300 kV, you only need 2 cables. So you don't need a large wave clearance and so on. Right. Now, this is a scheme in US between the Petersburg and San Francisco. Remember, these San Francisco area is heavily congested. So these are the network congestion before this HVDC link came into the practice. Then the Siemens put up this HVDC link using a special technology using insulated gate bipolar transistors. But they used the Great Lake to make it a submarine link. By doing that, they could justify the cost. And you can see here what happened after they put up the DC link. Obviously, today we have very large HVDC schemes, ultra high voltage schemes. You can see the people down there. Those are people compared to the large transformers. This is the largest scheme. It's a 12 gigawatt capacity. It transmits over 3,325 kilometers at a voltage of 1,100 kilowatt. Now, the requirement for a smart inverter is increasing day by day. Now, this one shows a feeder in Germany. Now, early morning, the voltage at the feeder was around 1.02, and the feeder absorbed reactive power from the grid around 1,500 kilowatt. But as the day passes, you can see somewhere around 10 o'clock, it's no longer taking power from the grid because the rooftop solar is providing all the active power requirement. But as the day comes towards the midday, you will start seeing the power going in the reverse direction. This is called the reverse power flow, which has increased the voltage to 1.09 per unit. And now this is very much closer to their statutory limit. So we need to do something. And also you can see that there was a cloud cover here, and that directly affects the power transfer capability. This is the visibility issue I was talking about. So the best way to overcome this is to utilize your inverter as a STATCOM, static VAR compensator. This is the simple phasor diagram of the STATCOM. So today the IEEE 1547 demands inverters to provide the reactive power using its STATCOM facility. So at rated power, you must at least provide 44% of this yours rated to the grid reactive power. So the smart inverters, of course, work with SCADA RTUs, because where you not only have one central inverter, in many cases you have many inverters, so you need to talk to each of them, take the command from the grid, talk to each of them and schedule their reactive power accordingly. You also can do some more coordinated control using optimum power flow and using a smart grid controller. And if you have on-load tap changes, you can do better in these distribution networks. And distribution automation and management is becoming another important technology to overcome the resilience, to provide the resilience. This is a device built by a company called SNC in California. In fact, I managed to visit their place. They basically have a wall-mounted devices they open automatically. They have their own current and voltage sensors, and there is a agent-based controller. So you can do a agent-based controlling approach for a distribution network using this distribution automation scheme. Of course, in the future, we can start seeing the mini grids, and the mini grids can be either have normally open point or the soft meshing devices, such as this one. This is a soft meshing device. So there are a lot of work going on, but I haven't seen single actual usage of this soft normally open points. But there are mini grids coming up, they are flexible, and they also can be used to empower the people. If you are using it as a consumer grid, and power losses can be minimized. Now, this is a mini grid establishing in King's Cross in London. They are using 2,500 residential area and 500,000 square foot commercial area. This is, in fact, not only, if you look at it, it's a district heating, electricity, fiber, water, and gas. Not only one network, many network integrated together. There are microgrids also coming up. Remember, some of these microgrids can be DC. If you use DC instead of AC, then in your laptop computer, you don't need most of these. You don't need a rectifier. You don't need the perfect control capacitor. So that increases the efficiency. Same thing with your air conditioner. You don't need any of these filtering and the AC to DC conversion. You can directly feed your motors using your DC. And now you can even get rid of the IGBT inverters if you use the brushless DC motors. And other thing is, when you are trying to convert DC into AC using an inverter in a solar PV system, when it is operating closer to its output, yes, efficiency is good, but in the early morning, efficiency is very low. So that is the problem. So why not use DC? So, and also, if you look at the modern data centers, most of the things are DC, even though it's powered by AC. You can power the entire data center using DC. So in fact, this is one of the research we did. We developed a DC microgrid, and we developed a special energy management system for this. Of course, we couldn't test it in a real world scenario. And in Australia, they have introduced a virtual power plant. This is like each home is connected together to form a large generator. So in this particular one, there are 90 Tesla batteries, 10 Samsung, so 100 homes are connected together. New and existing solar and local repository controllers to connect these houses together. Now, if you have one house, if there is a frequency change like that, that house will increase its power output in kilowatt, as you can see. But when you have 100 houses, you can get a megawatt level response to reduction in the frequency. So that's another thing which is coming up today. And if you have not visited. Another technology we have integrated is the agrovoltaic, which is a power plant in Hantana, Kandy, which is basically one of my babies. So here the idea is if you are trying to put up lots and lots of large solar farms, they are going to reduce the food production, because some of the lands, if you go to the Yattakandia, you can see that there's a land which used for corn farming is now given to solar farm. So this is very dangerous. So we are looking at the dual use of land. Now these solar panels are semi-transparent, and the tea plantation is something like shading. It's a shade-loving plant. So these panels will let enough light to go through for the tea to grow. And we have now set up a AI-based system to look at the plant growth, the diseases, and so on. So you are welcome to visit this. In fact, one of the senior lecturers from agriculture, Chitra, she's working with me on this project. She's from Brunei University, but agriculture faculty. So this is another important area which is now coming up. So in conclusion, the greener solution supports sustainable economic growth, but there are 4Ds which need to be considered: decentralization, decarbonization. But when you are thinking decarbonization, we need to make sure that what we call the energy trilemma. If you try to decarbonize, the price will go up and the reliability will reduce. So we need to think about doing that in a more sustainable manner, and the digitization and democratization. So with that, I will conclude my session and hand over to the organizers for.
Yeah, so thank you very much for that insightful and inspiring session. I'm sure our audience has gained valuable knowledge from your expertise. So we will now move on to the Q&A session, and participants are kindly requested to share their questions through the Q&A option in the Zoom platform. So while we wait for the questions to come in, I'd like to raise one question on behalf of the audience, which is looking ahead in the scope of smart grid and renewable energy innovations. What skills do you believe that young engineers and researchers should focus on while developing if they want to be at the forefront of this industry?
And now, obviously, as you could see, the renewable industry was gaining momentum in last few years, but many government, not only Sri Lankan government, even the UK, they scrapped some of the offshore wind farms. So that is a bit challenging today in terms of going towards sustainable options. But there are new avenues which are coming up for young engineers to look at how to use hydrogen effectively, because one of the things rather than using pump storage hydro, you can use the excessive energy to break water into hydrogen and save it, and then use it during the night as a fuel cell. Now, this is a technology which is mature again, but we haven't done much in Sri Lanka. So I'm sure there will be enough avenues coming up for the young engineers to get into. But at the same time, as you could see today, PUCSL has called for public hearing to increase the electricity tariff. So that is happening. As with that, the CB may say that, no, we don't want to go into renewables anymore. We will reduce the renewable portion. So there is always this difficulty. So, but like geopolitics will play a big role here. If there's more fighting in the Gulf region, then we will again think of more renewables. So it's something at the moment. It's all bit what you called gray. So I wouldn't ask young engineers to put fully engage with renewables. But if you can look at the AI applications for these renewables, for example, as I told you, the agrovoltaic plant, we are now developing a digital twin for that. So there are lots of areas where lots of innovations our young graduates can do to promote the sustainable operation of our grid.
Yes, thank you. So, one question we got is, how will smart grids change energy distribution in developed and developing countries?
What did it say? How
will the energy transformation will affect the developing and developed countries?
Okay, I mean, today every country is struggling, I would say. As I said, the geopolitics plays a big role in the energy sector. So, whether it's a developing country or developed country, only difference is we use energy at a very low levels. For example, average energy consumption of a household in Sri Lanka could be like 80 kilowatt hours per month. This is the average I'm talking about. Whereas if you look at a country like UK, the average will be 1,000 kilowatt hours. So the energy requirement will be different. So our problems are the same because when you look at the proportions, they will be both like developing or developed countries work in kind of both work in the similar arena. So I can't see big difference. Other than of course countries like China is aggressively putting money into renewables, but US is doing other way around. So it's a very difficult picture today.
Yes. So another question, which is that there is a new energy storing method used in some countries that they use huge sand tanks, which can be heated and store energy as heat. So does that type of storage possible in Sri Lanka?
Huge sand tanks. Yeah, we had a project. If you could remember, I was involved in a project with it was Tilak Simbalapiti and myself. We did one of those consultancy projects, and we were trying to use this. It is possible, obviously, but whether they will. I mean, the one thing is, of course, we don't have heating networks. We are mainly having isolated air conditioner. If we have AC networks, these kind of heat storage will become more prominent. I mean, for countries in winter, countries having winter climate, heat storage is economical way of doing things. But for Sri Lanka, I don't know. We were trying to do one as a pilot, but we never did it.
Okay, so another question is, what are the things that is needed to ensure cybersecurity in them?
Okay, I mean, I had a PhD student, and his job was he was funded by a company, and all they wanted to do is for him to get into their system and hack it, and that was his PhD. So these young minds now can do anything. So it's going to be tough. The utilities are very carefully thinking about various ways to make sure that cyber threats are minimized. But I'm sure with more and more ICT involvements, it's going to be tough. That's why, of course, for critical infrastructure. None of the utilities in the world use corporate network. They have their dedicated networks. For example, if you are working in National Grid, UK, you can't even access your email from home. Only when you come on site, you are allowed to access your emails. So that way, of course, they are keeping their network isolated from corporate network completely.
Okay, so moving on, another question based on Sri Lanka. So does Sri Lanka has an economy to have a renewable energy-based generation? And are we ready to take such risk corporate and with uncertain behavior of renewable resources?
I mean, there was a document which I was sharing that committee. We look at a pathway to add 80% of renewables. Later on, it became 70% of renewables. So we developed a document which we very carefully said that if you wanted to go towards that, we need to develop certain technologies and not as everything that I was talking about. For example, the smart inverter should be a must. Right now, IEEE 1.7 is mandating smart inverters. So we developed such a document. So if we had used very well planned methodology, of course, the document that our committee developed was thrown to the bin because the government then government didn't like that proposal. But I think we need to plan. We need to have a very clear picture how we are going to go for renewable future. You can't launch the rocket without a launching pad. So we need to first develop that launching pad while we slowly build in the bits and pieces of that rocket.
Thank you very much, sir. So I guess that's all Q&As for this session. And with that, we bring today's session to a close. Once again, a heartfelt gratitude goes to our wonderful resource person, Professor Ekanayake, for taking his time and enlightening us with such valuable knowledge from his expertise. So once again, this is a reminder that this is just one of many opportunities that we have planned. We are excited to announce that our next webinar on sustainable solutions for smart and resilient infrastructure by Professor Rangika Halvatura will be held on 18th of September. We warmly invite you all to join us for yet another enriching experience. So stay curious, stay engaged, and keep learning. Thank you once again for being with us today. Have a great day.
Sure. Pleasure. Good night.
Good night.